Before all, I would like to thank the organizer of this Turbo Expo 2022 Congress for the chance to present this work. Today, I will be talking about the methodology for the pitch controller wind prediction system in small wind turbines. I'm Oscar Roberto Lara Mendoza, and my co-workers and professors are the PhDs Juan Carlos Jauregui Correa, Ernesto Chavero Navarrete, and José Román García Martínez. We are from the engineering faculty of the Autonomous University of Querétaro in Mexico. You can find the complete paper in the proceedings of the Congress. I would also like to thank the reviewers for their helpful comments for the better development of the paper. And again, I want to express my appreciation to the organizers for the space to present this work. What is going to be discussed in this presentation? Well, we decided to divide this presentation into 6 essential points that we had already reported in the written paper. Okay, so the presentation focus are these 6 topics. The first one is the motivation of the work. Why were we decided to work with pitch control topic? Then we present an introduction that shows the audience the background about pitch control in wind turbines. After that, we review some of the relevant papers that we can find in the literature of all the topic. After that, we present the methodology that is the essential and fundamental element of this study. Finally, we present the results and some conclusions. The motivation behind this work is the development of the methodology for pitch control in small wind turbines. But what is the problem? Well, the problem is with the pitch system. When we send the control signal to the mechanical system, the blades don't arrive quickly at the desired angle. So, why is relevant in small wind turbines? Well, it's relevant because normally the small wind turbines are installed at low altitudes. Okay, and when we have low altitudes, there are changing wind patterns, or in other words, there are wind gusts that are not exploited. Okay, the normal procedure for wind turbines is that when we have wind gusts in the area, we slow down the system, and when we slow down the system, we waste a lot of amount of wind. Okay, and this is the motivation of our work. Like an introduction, it's important to know the classification of the wind turbines. We can classify according to their axis of rotation or rotational axis, or according to their size. If we classify according to their axis, they can be vertical axis wind turbines, or also called bow types, and horizontal axis wind turbines, or also called hot type. Normally, the hot type wind turbines have a higher efficiency than the vertical ones. It is also important to mention that the hot types wind turbines is the most manufactured worldwide. But on the other hand, the small scale wind turbines are classified when you have a wind turbine with a capacity of less than 100 kilowatts, when you have a turbine with a swept area of less than 200 square meters, and the voltage work is below the 1000 volts. The figure on the left shows the representation of the two types of existing turbines. In this paperwork, we presented a horizontal axis wind turbine that are also a small scale wind turbine. Here we present another important background that we need to know for a better understanding in the topic. It is essential to know what a pitch control does in a generator system. Well, the pitch control tries to keep the generator rated speed when there is wind speed above the allowable in the system. Here is the representation of how the pitch system acts on the blades. It is seen that the rotation of the blades is made on the same axis of rotation. Okay, below we present a diagram of with the four zones of operation in wind turbines. The zone 1 is identified when the wind is insufficient to move the generator rotor. Then the zone 2 comes when the starting speed is reached and finishes at the rated speed or nominal speed. It is in this zone when the maximum power point tracking control must be performed. This is for reach the optimal operating point quickly. Okay. Then in zone 3, the generator rotation speed must be constant, even if the wind speed is higher than the nominal. Here the pitch control is performed. This is the important zone for us. After that, the cutoff zone or zone 4 is triggered if the wind speed surpasses the controllable pitch speed. When we are in this zone, the blades must be positioned at 90 degrees, also known as a flag position. In this zone, the blades function is as an aerodynamical brake. Okay, this slide presents the Lara acquisition system that some authors use as a method of prediction system. The LiDAR is the abbreviation for light detection and ranging, and it has a lot of applications. But here in the wind turbines is utilized as a predictive of wind data information. So the system is used as a tool to predict the wind speed and direction before it hits the blades. Okay. It is usually installed in the nacelle of the wind turbine. In other words, at the top of the wind turbine. It consists of a laser beam that bounces with the wind particles, and when it returns to the receiver, it calculates the wind speed and direction. These features allow the blades to be positioned in time before being impacted. Here we present some illustrations that shows that some authors are utilizing this system for predictions in wind speed and direction. You need to know the most relevant papers that we found in the literature for this topic. We examined several papers related to the subject. In these 4 papers, the author report simulation results. These papers have in common a LiDAR system as a wind data acquisition tool. The proposals illustrate various types of predictive controllers, but all of them are similar in terms of the proposed predictive controllers. All of them are based on a feed-forward controllers, like they call. In these proposals, the authors use the PI controller as the basis of the pitch system. In general, the authors prove that their proposed predictive systems improve the speed control in the generator and reduce the loads on the blades. Like I say, the proposals are commonly described as feed-forward feedback controllers. Okay, so here are the most relevant literature that we found in this topic about predictive systems for pitch control in small wind turbines. It is also important to mention that these other 4 papers are relevant for work, and that is because the authors show experimental results. In other words, they prove their controllers in an experimental platform. The findings correlate with those presented in the simulations. The authors have in common that they conclude an improvement in generator speed control considering the proposed prediction system. And the proposed prediction system based on a feed-forward control um, and based on a LiDAR acquisition system. Specifically, one of the researchers proved that an anemometer measurement system is better for the speed control of the generator compared to a LiDAR system. So, based on this paper, we decided to use an anemometer measurement system. And that is because its simplicity, its effectiveness, and it has a lower cost. And it is proved that with anemometer measurement system, we can improve the results in a prediction system. So here are the presentation of the literature of these 4 works. You can access them in the complete paper that are in the proceedings of the Congress. This slide is the beginning of the methodology that we developed for this work. The idea of this work is to have a metmast installed upstream of the wind turbine that sends the wind data to the pitch controller. In this way, the mechanical pitch system will have enough time to position itself correctly at the desired operating angle. So, how do you choose the distance at which the metmast should be installed? For this, it is necessary to make a historical analysis of the wind data in the area. It is essential to know the maximum speed and the direction of the wind. So, we analyze these conditions based on 7 years of historical data, and the results that we found is that we have a maximum wind speed of 15 meters per second with a predominant direction between 70 to 110 degrees. In other words, the wind's coming from the east to the west. In this image, you can see the wind rows with the predominant wind direction coming from the east to the west. This other image shows the actual area with the required distance between the metmast and the wind turbine. You can see that we need 354 meters upstream of the wind turbine to correctly predict the position of the blades. The following slide explains how we obtain this design distance. So we can calculate the distance between the metmast and the wind turbine according to this relationship, where D is the distance design between the wind turbine and the metmast. Vmax is the maximum velocity collected from the statistical analysis. And T is the time it takes to position the pitch system in a range of 0 to 50 degrees. So we do the work, and we conclude that the blades need 22.8 seconds to move from 0 to 50 degrees. Like you can see here in this representation. 0 degrees and 50 degrees is the total range that the pitch control operates. We use the feedback encoder in conjunction with the microcontroller to check this time. So this 22.8 seconds is the one that we need for the relationship shown in here. And Vmax is the 15 meters per second that we obtain from the statistical analysis of the wind. What else? We installed, like I said before, the metmast 354 meters upstream of the wind turbine, according to this relationship. We report that the relationship shown here is well used for short range prediction forecast because of the persistent method or Navier predictor theory. The Navier predictor said that the wind speed at time t will be the same speed in a short period of time. So, in base of that, we can postulate that this relationship is okay for design. The next step of the methodology is to describe the wind acquisition system. We installed a 30-meter high med mast located 354 meters upstream of the wind turbine. The tower has two measurement branches, one at 15 meters with two anemometers and one wind vane, and the other branch is at 30 meters with two anemometers and one wind vane. Okay, these instruments are for collect the wind speed and the direction. We added pressure, temperature, and relative humidity sensors to complement the wind information data. The anemometers and wind vanes operate at a working frequency of 1 second. The figure on the right shows the met mass at the installation site. According to the predominant wind that we found on the statistical analysis from east to west, we need and we must to orient the arms of the anemometers to the north and south for a correct acquisition of the velocities. Well, here we present another section of the methodology, that is the free wind flow validation. It is essential to prove a free wind flow in the wind turbine area. This is because the existence of turbulence due to the surrounding land and buildings decreases the wind force in wind turbines. So we did a computational flood analysis was performed to confirm no interference between the surrounding buildings and the wind turbine. These are the data that we use for this CFD analysis. We use 4.9 meters per second and 18 meters per second wind speed were used to validate this simulation. And the direction of the wind is in the predominant statistical analysis result, that is from east to west. So in this analysis was found that the buildings are not obstruction to the free wind flow. Next in the methodology is to highlight the particularities of the case study discussed in this paper. We installed the wind turbine in Querétaro, Mexico, which has an altitude of 1975 meters above sea level. The rotor that we use is a three-bladed rotor of 6.4 meters in length with 260 kilograms each. The height of installation of the wind turbine is 18 meters above the ground. This is a small-scale wind turbine. Also, it's important to mention that we use a generator, a permanent magnet generator, with a capacity of 14 kilowatts. The nominal speed of this generator is 14.6 radians per second. The pitch system moves the blades through a DC gear motor coupled with a warm and inspired bevel juice, like is shown in this figure. The speed reduction between the DC motor and the rotation of the blades is 3600 to 1. In other words, for each 360 degrees of rotation of the blades, the DC motor will give 3600 turns. We designed the very high reduction to avoid backlash in the blade position once the desired position is reached. So this is the basis that you need to know for this case study. The next step in the methodology is the controller proposal. Here you can see the controller that we proposed for this work. This controller is integrated with three well-defined modules. The first one is the data preprocessing, or also called the acquisition of the wind speed through the empirical mode decomposition, also called EMD technique. After this module, we have the computation of the reference angle by the fuzzy system. And after that, and finally, we have the conventional PI controller. Is employed for the angular positioning of the blades. In this step of the PI controller, It's important to mention that the pitch system is modeled as a second order system with the addition of a gain. This gain represents the total reduction between the DC motor shaft and the output of the rotor blades. So this is the representation of the pitch system, the electromechanical pitch system, like a second order with a addition of a gain. It is noted in figure 7 that the control system output is the angular position of the blades. The feedback is done through the encoder of the motor. Also, it's important to mention that the pitch control is achieved in the range of 0 to 50 degrees, which is the typical working range of this system, like we discussed before. The EMD preprocessing technique is the first model that we found inside the controller, one of the main contributions of the research project. It is well known that wind measurements are intermittent and chaotic, like we see in this figure. It is impossible to use this wind data with high frequencies in a prediction system, such as the one proposed here. So we need a preprocessing of this data. There exist several methods, but for this purpose, but we selected the EMD method or empirical mode decomposition because this is intuitive, simple, adaptable, and operates directly on the dataset. The EMD technique can outperform other methods in processing nonlinear and non-stationary data. And that's it because the EMD decomposes a time series of signals into a finite and small number of intrinsic modes and residual. These modes are defined as intrinsic mode functions. In other words, the EMD technique decomposes a time signal into a finite number of subsignals with components of different frequencies. That is why we select this technique. The raw wind speed doesn't provide helpful information for a control system. However, with the EMD preprocessing, subsignals with different frequencies components are obtained. So these EMFs have a more significant benefit in a control system such as the one proposed in this paper, because they isolate the wind data that the controller can track. The figure shows how the original data wind have high frequencies. This is not okay for our purpose because this is not fed the pitch controller. If we fed the pitch controller with this signal, we doesn't have a nice and a smooth response of the controller. So the idea is to decompose this signal in its different modes to put it back together, but adding only the modes of interest. In other words, we removed high frequencies from the original signal with this method. The algorithm used is shown here. It consists of two iterated loops. The idea behind the first step is to identify all the maximum and minima of the original signal. The second step is the joining of all the maximum and minima by using a curve, or also called an individual envelope. Then there's a third step. We calculate the average between the upper and lower curve. After that, we calculated the residual, subtracting the original signal minus the calculated average. Finally, we need to check if the residual satisfies the stop condition. Normally, the stop condition is between 0.2 and 0.3. If we satisfy the residual condition, we enter in the output loop, that is this. So if we satisfy the stopping criterion, we have the freeze mode of the original signal, and the cycle starts again. The algorithm stops when there are no more than 2 minima or maxima in the mode signal. In this figure, we can see the modes that we obtained by decomposing the original wind signal with the algorithm proposed in the previous slide. The first modes, mode 1, 2, 3, 4, and 5, still have high frequencies. This is unnecessary for us for control. These modes represents the noise in the signals, so we delay this. We don't need this for control. We need the modes 6 to 12 to represent the behavior of the original signals. So with these 6 modes, we can represent the original signal and its behavior correctly. Okay, a fuzzy control system is an alternative when the mathematical model of the process cannot be determined. That is why we use this system as a process of the reference speed channel. In our case, we have as an input the wind speed preprocessed by the EMD technique with 5 linguistic variables called small, medium, big, and very big wind speed. And as an output, we have the reference pitch angle. The reference pitch angle is named no movement, small movement, medium movement, big movement, and very big movement. Okay, these are the inputs and outputs. We categorize this according to the wind speed. This reference pitch angle are categorized according to the wind speed. There are one-to-one relationships between inputs and outputs, and the inference method that we use is the centroid method. 3 main aspects have been demonstrated here. The first one is the preprocessing of the wind data using the EMD technique. This technique was done according to the actual wind conditions upstream of the wind turbine. In this figure, we can see 2 wind signals, the original that is in black and the reconstructed that is in red. It can be appreciated how the original signal has high frequency components with abrupt changes in intervals of up to 1 second. This original signal is not suitable as a speed reference for the PI controller due to its fluctuating nature. This is why the signal must be reconstructed so that the PI controller can follow the wind speed curve. It can be seen how the curve in red follows the original signal closely and with small changes in the wind condition. The preprocessed signal in red color is the one that we use to feed the pitch positioning system. The other result that we show here is the angular reference position that we obtain with the fuzzy system. These tests were performed in simulation using MATLAB software. In this figure, we can see how the angular position is the output of the proposed fuzzy system. As described in the methodology, this one-to-one relationship system is responsible for selecting the reference position that fits the PI controller. If we observe both the reconstructed wind speed signal in the previous slide and the curve in this figure, we can see how the one-to-one proposal of the fuzzy controller is fulfilled. Here we present the last result that we obtained, and this is the angular position output of the PI controller. In this figure, we can demonstrate that the PI controller can follow the reference position commanded by the fuzzy system. You can see in this figure at the bottom that there are slight difference between the reference position and the actual position of the rotor blades. However, they are not significant. We have 3 different conclusions. The first one is that the EMD technique and the open loop fuzzy system provide satisfactory outcomes for wind data processing. The next one is that the mathematical modeling for the pitch system employed for the PI controller response simulation is suitable. And the last one is that we need to confirm that the tests made in simulations correspond to physical experiments for future work. Thank you all for the attention. you can find in the conference proceedings the complete work.